Okay, we got test tomorrow over Chapter 9 on the integration. There's 20 problems, so each one will be worth 5 points. Now, unfortunately, they're not all about the same difficulty. Well, fortunately, maybe. Some are easier, but even the hard ones are worth 5 points. Or the hard one, or, well, maybe there's more than one hard one. But anyway, 20 points, or 20 problems, 5 points each. All of Chapter 9, so a little bit shorter, much more focused content this time, so hopefully that'll be a little bit easier for you than our last test. What we're going to do today is talk about what to expect, and I think you probably have a real good idea. The first several sections of Chapter 9 will be looking at antiderivatives. So there's first few problems on the test will be find the antiderivative, whether it's just straightforward using the power rule or possibly some substitutions, some trig antiderivatives, exponential e to the x or something like that, logarithms, 1 over x, antiderivative is natural log of x. So lots and lots of different possibilities there. And then we started building up to get to the definite integral. So a little bit of the what we talked about there. Summation. Okay, there will be no problems dealing with summation like we had on the worksheet. Now, we will be dealing with summation a little bit when we get to the definition of the definite integral, but nothing in particular, just the summation problems. We did talk about area under a curve, and at first we began by approximating using so many rectangles. Now, on the worksheet I gave you, I had you do 4 rectangles and then turn around and do 8 rectangles. We won't do the 8. It'll be more like 4. So I do want you to get done tomorrow. But 4 rectangles, possibly left endpoints, possibly right endpoints. So we looked at both of those, and key there, figuring out what delta x is, what our width is, and for that, how do we calculate delta x? Okay, the b minus a, however long the interval is, from 0 to 2, we'd have 2 over the number of rectangles. So if it was 4 rectangles, 0 to 2, each width would be a half. Maybe it's from 3 to 11. Make sure it's somewhat nice. If it's 3 to 11, our width would be what? With 4 rectangles. Okay, the width would be 2. So maybe it's a half, maybe it's 1, maybe it's 2. I'll try to make it somewhat nice, but not too nice. I want to make sure you guys can do these. But anyway, we started talking about the area under a curve, approximating it using n rectangles, and so there'll be a few problems like that. Then we got into the definition of the definite integral. And that definition, definite integral here from a to b. Now, I'm not going to have you memorize the definition, but you do need to know how to work through a problem like this. And some other details, but basically your delta x sub I, we said the widths could be different values, but we're going to want to keep it as simple as possible, so we can make all delta x sub I the b minus a over n. Okay. What's the c sub I represent? C sub I is the x value for the ith interval. Okay, that's going to be our sampling point. That is what we'll plug into the function when we think of height of that rectangle. And most of the time, the easiest representation for c sub I is what? We let it equal the x sub I, which is technically the right endpoint. So what we're going to have to do, the biggest problem, most amount of work here, is figuring out how x sub I is represented, and then plugging it into the function. Now, on the worksheets, we had anything from a linear function to a quadratic. I will limit that to just a linear function. Quadratic would be okay, but it's yet another formula for you to try to memorize. But for that, once we find x sub I, once we plug it into here and simplify, then we apply our summation. And those summation formulas, the two formulas that you'll need to know: summation of a constant from 1 to n is what? Okay, that constant times n. And in these problems, n will basically be in general, and our limit will turn into a limit as n approaches infinity. Because we're allowing all of our delta x sub i's to be equal, then our what we call the norm, or the mesh approaching 0, can be implied that n is approaching infinity. So formula for constant, summation of a constant, c times n. And then the other formula, little bit more involved, the summation of I, as I goes from 1 to n, is what? Okay, the n times the quantity n plus 1 all over 2. So those two formulas will be used after we plug in our x sub I or c sub I into the function. And then you got just a lot of algebra to work through, a lot of simplifying, and finally taking the limit as n approaches infinity, and that gives you the value of this definite integral. Now, I will give you a problem saying use the definition of the definite integral, and I do want you to show me those steps, not just show the answer, because by now you know how to do the shortcut of it, and it would be good to check using the shortcut. Make sure you got it right. But I do want to see all of these steps on that type of problem. Okay? So lots of steps in here, and because of that, probably only one problem like that on the test. But so let's see, at least one or only one. We'll say only one.
For this type?
For this type, yep. Okay. So then we finally got to see the fundamental theorem, which is the biggie in calculus, tying the derivative into the definite integral and evaluating a definite integral. Evaluate. If I could spell right, that would help. So lots and lots of examples of evaluating definite integrals. And again, with that, the fundamental theorem, simply find your antiderivative and then evaluate it from A to B, which again means evaluate f of B minus f of A, and there's your shortcut. Now, we also talked a little bit about how the definite integral represents area, and if we have area under some curve and above the x-axis over some interval, well, to calculate the area here, what would we do? Okay, it would be the definite integral of your f of x evaluated from A to B. So immediate application here for the definite integral, and in fact that's kind of how we defined or developed the definite integral, was with the area. So those two types of problems are kind of interchangeable. Now there's another type of problem we talked about with area. That was given the graph of f of x, I'll just kind of make one up here. Oh, that's supposed to be a straight line, but you guys know that. So if we're looking for the integral of f of x, let's say from, let's go -3 up to 5. How would we do that? Okay. Well, first of all, we need to recognize the function. Part of it is below the x-axis, part of it is above. So we kind of have to separate it into those parts. From -3 to 2, we can find the area represented by that figure, or we may need to separate it into parts. And it would help if you had some y values there too, I guess. So we'll make that -1, -2, and then we'll make this up to 3 there. So area, well, whether you do, I guess this would be one trapezoid. If you know the area of a trapezoid, you could do that. Or you could simply split it into, that's supposed to come down here, two triangles and a rectangle. Calculate the areas there. This area would be what? The triangle. Okay, 1/2 times the base times the height. So area of that part would be 1, but when we translate it into the definite integral, we get what? -1, because it's under the x-axis. Then the rectangle,
6.
okay, so 6. Again, because it's under, we go -6. And then finally this part, this triangle, again, an area of 1. Okay, so from -3 to 2, integrating that function, we get a -8. And then from 2 over to 5, to finish out the definite integral, well, let's see, we'd have area here. Okay, we'd have 1/2 times the base of 2, so 1/2 times 2, and then times the height would be 3. Area of that triangle is 3, and then the rectangle would be what?
3.
Okay, another 3. So from 2 to 5, we get 6. So overall, the integral would be what? -8 plus 6 would give us overall integral of -2. So area translates to our definite integral depending on where the area is. If the area is above the x-axis, we get a positive value for the definite integral. Area under the x-axis, we get a negative value for the definite integral. Okay?
Are they all going to be nice like that, or are they going to...
Graphs like this will be pretty nice. You'll only need to worry about triangles and rectangles. So I'm not going to throw a ugly curve at you on those types. But okay, that's pretty much it. Any particular questions? Any problems that we need to look at? Okay, we'll take a look at number 11 on this last worksheet. Find the area below this function and above the x-axis. So one of the problems with finding area, sometimes we have to figure out what the endpoints are going to be. And that one, this would be where, let's see, well, try to graph it, but where is the y value equal to 0? Is basically, when we talk about the x-axis, it's the same as saying y equals 0. So solving this equation, let's see, with the square root in there, several different ways to do that, but add the x. And then usually when we have a square root in our equation, we need to square both sides. So that'll give us x squared equals, now it's not just squaring the square root, but square 2 times square root of x. Okay. And then, well, now we're dealing with a quadratic. So x squared minus 4x equals 0. And from there, factor if possible. I think you can kind of see where we're heading already now. So x equals 0 and x minus 4 equals 0. So our interval, as we look at the graph of this, when x is 0, y is going to be 0, and when x is 4, y is going to be 0. And we can also check that, plug 4 in for x, and we do get y equals 0. And the graph, well, whatever the graph looks like, doesn't really matter. What we're looking for, area below this and above the x-axis, or we can say from 0 to 4. So the integral, look at the definite integral from 0 to 4 of okay. Questions up to that point? Now, to do the integration, we'll need to find the antiderivative. And, well, square root of x, we need to do what to? Change that to x to the half power. So we'll have, let's see, we'll have the 2, and then integrate x to the half, and we get what? Okay, x to the 3 halves over 3 halves. And then integrate x, we get x squared over 2. We go from 0 to 4. Now, anytime we integrate and have these nice little fractions, we probably want to rewrite that as we go, but dividing 3 halves would be the same as multiplying 2/3. So 2 times 2/3, we'll have 4/3 for that part. And then we can start evaluating our definite integral. 4 to the 3 halves minus 4 squared over 2. And then minus, well, one thing you really have to watch with the 0, many times it just comes up to be 0. Plug 0 in this case, yeah, we just get 0. But there's once in a while when you have a 0 here, we're not going to end up with just a 0. So make sure and check that. Don't just automatically assume it's going to be 0. Okay. Okay, well, to kind of get a little better simplified value, 4 to the 3 halves. Remember, the half power is the square root, and 3 halves, we could say 4 cubed and then take the square root, or how about square root of 4, then cube it. And of course this one's 16 over 2, that's going to be 8. Well, 4 under the square root will be 2. 2 cubed is 8. And then, let's see. Well, this is where you start to get lots of work. Fractions, we'd have 32 over 3, and then 8, or 8 over 1 would be, what, 24 over 3. And we end up with 8/3, 8/3, 2 2/3, 2.667, something like that.